Throughout the school year, we'll be using a program online called ExploreLearning.com. They have online simulations that allow you to be able to kind of look at things in a way that we normally wouldn't, because here we're looking at atoms. We're looking at the relationship of the atoms. And so they call their simulations gizmos. And so this gizmo is on ionic bonds. And we're going to start by talking about sodium and chlorine. Sodium has a valence electron number of 1. It has 1 valence electron in its outermost shell. It is not happy with that. Now, right below that is its second shell that is completely full. But as it stands, its third and outermost only has 1 electron. And remember, the goal is to have 8 to be satisfied. If we look at chlorine, chlorine has 7 in its valence. It's so close to being happy and satisfied with 8. And so the most obvious thing to do then with these two atoms would be for sodium to donate that electron to chlorine. There it is. Now sodium's second valence, which was originally full, will be its new valence, giving it a +1 charge because it lost an electron. An electron has a negative charge. So when you are neutral and they're all balanced, but you give one away, then you become a positive ion. Chlorine, who was neutral initially, accepted sodium's electron and therefore now has become a negative ion. And so when we put them back into motion, we can see that the two are magnetically attracted to each other. Opposites attract. So covalent bonds are different. Co means together, valent means valence shells. Here we have the small atoms known on the planet as hydrogen. Hydrogens only have 1 proton in the nucleus and 1 electron in their shell. They also only have a shell that can hold a maximum of 2 electrons. So if both of these hydrogens are not satisfied alone, then they can both agree to share. So we're going to share over that way. We're going to share over this way. And what will happen is now the shared pair will rotate around the valence of both atoms, and both atoms will be completely satisfied. So if we speed that up, we can see how those electrons are moving. Remember, there was not a give and take. This was a complete sharing of a pair, a shared pair. So here we can see that with hydrogen gas, also known as H2. Let's look at water, because water is so often used as the poster child for the covalent bonds. So you have 2 hydrogens, each with 1 valence. Each needs 2 to be satisfied because it only has 1 orbital. Here we can see oxygen. Oxygen has 2 orbitals and its valence has 6 electrons. It's looking for 2 more. So instead of giving and taking, the hydrogens and the the hydrogen and the oxygen will simply share. So this hydrogen will share with this oxygen. This hydrogen will share with this oxygen. This oxygen will share with the hydrogen. And she will share with the other hydrogen. Sometimes these are tough to move around. There we go. Now watch what's going to happen when we turn on the orbitals and we see how the electrons move. Now the electrons are moving around all 3 orbitals, each hydrogen only experiencing 2 at a time because that's its maximum capacity. And right about here, the oxygen feels all 8 electrons. So in a covalent bond, you have an overlapping of the valence shells. There is a sharing of electrons. It's not as strong a bond as an ionic bond, but it is a very solid bond when it comes to forming molecules in compounds.